So we've learned recently that you can reinterpret Newton's laws of motion using the idea of momentum, and you get kind of a different viewpoint on them. In this video, the question is going to be, can you do the same thing with rotational physics? And the answer is yes. Just as there is a concept of momentum, let me just write it down here to remind you, momentum, which is P, and the equation for it is P equals mv. Well, we'll get to the equation later. We have the momentum P. In the same sense, for rotational physics, we have what's called the angular momentum. Pretty self-explanatory name, and the symbol for that is L. So if we think in terms of the angular momentum, then we can reinterpret the laws of rotational physics in the same sense that we reinterpreted them with regular momentum, or as it's more properly called, we're going to call this one linear momentum when we are being careful to distinguish it from angular momentum. Okay, so first of all, the defining equation, which I was getting ahead of myself on a moment ago. The defining definition for momentum is P equals mv. So what's the defining equation for angular momentum? And actually, you can probably guess what it is if you think about it for a couple minutes, because it's actually the same equation. Momentum is mv. What's the angular equivalent of mass or inertia? And the answer is moment of inertia, I. And what's the angular equivalent of velocity, v? And that is angular velocity, omega. So it's really the same idea. It's the inertia times the velocity, whether you're calculating linear momentum or angular momentum. So the starting defining equation for the angular momentum is I times omega, moment of inertia times angular velocity. There's another way that people often calculate angular momentum, which is also worth mentioning. This one is especially used if, for example, you have an object moving in like a circular path, like a small object moving in a circular path rather than like a big object rotating somehow. If this guy is rotating at velocity v, and this circle here has radius r, we can use the same concept as how we converted forces into torques to convert momentum into angular momentum. So in other words, remember how when we calculated a force, a torque from a force, we would use only the tangential component of the force and then times the distance to the axis of rotation. We can use the same idea for angular momentum. We can do just the tangential component of the linear momentum times the distance to the axis of rotation. P is mv, so you could also write this as the tangential component of the velocity times L, or more conventionally, people will usually write this as mvr, because for circular motion, normally the velocity is already tangential, so you don't usually have to worry too much about that. The distance to the axis of the rotation is normally r, the radius of the circle that the object is moving in. But I want to show you that it's really the same concept as how we got torques from forces. Okay, so that's the starting definition of what angular momentum is. The next step is to think about how do you interpret Newton's laws of motion and things like that in terms of momentum. I may as well do this in the same video because this isn't going to be a very long discussion. There's really not a lot to say. In linear physics, we had Newton's second law as force is a change in the object's momentum, basically. So we had this as our starting equation. This is, I'm using the non-calculus version, so that means this is only true on average for the force, but it's delta P over delta T. By the same argument, the average torque on a system, because that's the rotational equivalent of the force, is delta L. over delta t. So forces change linear momentum, torques change angular momentum. So that's pretty obvious when you think about it. That's pretty straightforward. Then the other thing is, when we interpreted Newton's third law, we had the concept of conservation of momentum, that the initial momentum equals the final momentum if there's no external forces acting on the system, changing its momentum. And in exactly the same way, for the rotational case, we have conservation of angular momentum if there are no external torques. So the way that you handle conservation of angular momentum is exactly the same way as you handle conservation of linear momentum. So I'm not going to dedicate a special video to that. Just go back to your momentum conservation procedure and do exactly the same thing, but applied to angular momentum. And that's all there is to it. So angular momentum can be very complicated, but in concept, it's the same as dealing with linear momentum.